In this lesson, we look at single-slit diffraction of light. Here are the objectives. Now, in a previous lesson, we've looked at diffraction, meaning the spreading of waves into the shadow region when they pass around an obstacle or through a gap. Let's look at that now in more detail. This is the wave interference simulation from PhET. The URL is here at the top, and I've got monochromatic light shining through a narrow slit, shown from far away here and in close-up here. It's tall and it's narrow, and then we can see the pattern that it's forming on a screen over here in close-up down here. Now notice that again, the light is not making a pattern here that looks exactly like the slit. It's actually spreading into the shadow region. It's spreading quite widely. So this is an example of diffraction. Light has wave-like properties, and therefore it's behaving like a wave. It's spreading into the shadow region. It's diffracting. Now notice a couple of other things that I can change here. If I change the width of the slit, I'm going to make it wider. What I want you to do is take a look at this dark region and this dark region. We're going to call these the first minima on either side. This is the central bright band. Then we've got a dark minimum here, and then a more narrow and dimmer bright band, etc. So I want you to watch this dark spot and this dark spot as I make the slit wider. So you can see I'm making the slit wider, and notice that those minima, those dark spots, are getting closer together. And as I do that more and more, they're getting closer and closer, so I'm crowding more and more bright fringes in from the side. Again, if I narrow the slit, those minima move out to the side, have a greater angular separation, if you want to think about it that way. Also notice that there's actually diffraction happening in both the horizontal and vertical dimensions, but in the horizontal dimension it's much more pronounced, and that's because the slit is narrower here. As the slit gets wider and it becomes more square, you can actually see that the diffraction in the vertical and horizontal dimensions gets more and more equal. But when I have a tall, narrow slit, I see more diffraction in the horizontal dimension. Another thing I can change here is the wavelength. I've got long wavelength red light here. It's monochromatic. I'm going to shorten the wavelength, and again, watch what happens to those two minima. As I shorten the wavelength, moving towards the violet end of the spectrum, those minima come closer together. So we've seen that there are two things that I can do to bring those minima closer together. I can make the slit wider, or I can decrease the wavelength. So the pattern that we saw was a wide, bright, central bright fringe or band, and then we saw a narrower bright band that was dimmer, and then another one that was dimmer still off to the side. I can't draw the dimness very well here, but this is the brightest fringe in the middle, and it was wider than the others. If we graph the intensity, so this will be the intensity on the vertical axis, and the horizontal axis will just be the distance along the screen. So this is the center here. We get something that looks like this. We have a bright and wide central fringe, and then narrower and dimmer bright fringes off to the side. And they get dimmer as you go out from the center. And the same thing on the other side. So the pattern is symmetrical. Now, these were the two dark spots that we were watching, and we saw that we could move them in and out by changing the wavelength and changing the width of the slit. I'm going to call this angular separation here theta. So this is at positive theta, this minimum, and this is at negative theta. Now, turns out that the angle from the midline to the first minimum, that angle theta, is roughly equal to the wavelength divided by the width of the slit. So B is the symbol that I'm giving here to the width of the slit. And we saw that if we decreased the wavelength from red to violet, then these minima crowded in towards the center. So if I decreased the wavelength, I decreased that angle from the midline to the first minimum. We also saw that if I widened the slit, so if I increased B, then I also decreased that angular separation. So this is the equation that governs what we just saw in the simulation. To summarize the pattern then, light diffracting through a single slit has this symmetric pattern with a central bright fringe which has an angular width of 2 theta and is brighter than the others, and as you go off to the side you have these narrower bands that are less bright. And these have an approximate width of an approximate angular width of about theta, and we'll see why I say approximately in a moment, but they are narrower, about half as wide as the central bright fringe. And this is the equation that allows you to find the angle from the midline to the first minimum. Just be careful that this equation is helping you find the first minimum, in contrast to the equations that we saw for double slit interference, which are helping you find the angle to the maximum, or the separation of the maxima. So just be careful that here we're dealing with minima. Let's look in a little bit more detail where this equation comes from. We're going to zoom in very close up to the slit, and just like we did in the previous lesson with double slit interference, here we see the barrier. Now it only has a single slit in it, and the screen that we're projecting the light onto is far off to the right. So when we're very close up, we can treat the rays coming through this as parallel. Now, notice here that what I've shown is light coming from the top of the slit towards the screen and from the middle of the slit towards the screen. So this distance here, the whole width of the slit, that's B. But this distance here is only half of B, so this is B over 2. And again, these are parallel, and I'm going to draw my line like I did in the previous derivation for double slit interference from the center of the slit out to the screen, and we're going to call this angle theta. This is the angle that's going to be from the midline to that first minimum, which is what we are looking for. By geometry then, if I draw a triangle here, that's a right angle triangle, so there's my triangle that I've just shaded in. That angle there is theta, and this little distance right there, which I'm going to call x for a moment, is my path difference. It's the amount by which this bottom ray has to travel further than this top ray in order to get to the screen. Now, if you think about this triangle here, then the sine of theta is equal to x, the path difference, over b over 2. So x, the path difference, is equal to b over 2 sine theta. So in this case, our path difference is b over 2 sine theta. Similar process that we used to when we were talking about double slit interference, but now we're only looking at half of a single slit. Now, we want destructive interference in this case because we are looking for the location of the first minimum. And remember, in order to have destructive interference, we need to have a number of half wavelengths that's not an integer. The waves start out in phase here, so they're both cresting at the same time. But in order to have this one cresting where this one is at a trough when we get to the screen, we need this one to have gone a half a wavelength longer. In other words, we need the path difference to be a half a wavelength. Just 1/2 wavelength because we're looking for the first minimum. So for destructive interference, we want the bottom ray to have traveled 1/2 wavelength further so that it has a trough when the top one has a crest, although they started out both cresting here at the slit. So I now set this half number of wavelengths equal to my path difference because I want my path difference equal to a 1/2 wavelength. And rearranging this, I get sine theta is equal to the wavelength over the width of the slit. Now remember our small angle approximation. For small angles of theta, 15 degrees-ish or less, theta and sine theta and actually tan theta are all effectively equivalent. We've seen that in a previous lesson. So now I can simplify this and get the equation above. And so for the first minimum, when that angle is small, I can use this approximation, and this equation gives me the separation of that first minimum, the angular separation of that first minimum from the midline. Now above, I said that the other minima have an approximate width of theta, and I said approximate because really if we wanted to graph this accurately, what we would be looking at is sine theta is equal to different multiples of the wavelength over the width of the slit. So if I put an n there, now if this becomes 0, 1, 2, etc., solving this equation would allow me to find the location of all of the subsequent minima. So it's not exactly theta, it's actually sine theta. That's why I said approximate. But when we're just trying to find the first minimum, this equation is good enough because of the small angle approximation. Now there might be something bothering you about this derivation. Why did I pick the top point and the ray coming from it and the middle? Why didn't I pick other points? Well, I can continue by analogy. If this point here has a ray and this point here at the middle has a ray that are interfering destructively, I can do the same thing with a point just below the top and just below the middle. And then I can continue with a point just below that and just below here and repeat this kind of thing all the way down. So there's always a point in the top half of the slit that can be matched with a point in the bottom half of the slit that corresponds to it, and we can repeat the same kind of thing. And that's how it all works out that we get this equation. So I've only shown you for the top and the middle, but you can repeat that all the way down the slit. Now, let's talk before we finish about white light. So far we've been talking about monochromatic light, but if you shine white light through a single slit, you see an interesting pattern. In the center, all of the different colors of light show up, so you get a center white fringe. But the different colors of light have different wavelengths, and so they diffract differently. So violet light, for example, has a relatively small wavelength compared to the others, and so small lambda means small theta. We're going to get relatively little diffraction of the violet part of the white light. So it's going to have a relatively small angular separation and show up like that. In contrast, red light has a relatively large wavelength, at least compared to violet, and so it's got larger lambda means larger theta, larger angular separation of the fringe from the center. So the red light is going to diffract out farther. And as a result, we see this spectrum for our fringes with red on the outside and violet on the inside. And then I don't have all the colors of the spectrum, but I can fill sort of some of them in to give you an idea. You get this separation of the different colors of the light with this central white fringe and then the other fringes being separated out into colors. Note that I haven't drawn this at all to scale. These would be more crowded together, but I've just drawn it out like this to show you the separation. So that's a look at the diffraction of light through a single slit.